we're going to talk about radiation. And the reason we're doing this is to refamiliarize yourself with what the concept of radiation is, so we can begin the process of training you on the new equipment you received through a grant. When we talk about radiation, we need to begin with the atom. What is an atom? Well, atoms are considered the basic unit that makes up the building blocks of matter, matter being solid, liquid, or gas. It is when the atoms bond or unite that molecules are formed. Now, there are three parts to an atom: the proton, the neutron, and the electron. Now, the protons and the neutrons reside in the center of the atom, known as the nucleus, whereas the electrons orbit around that nucleus. When we talk about protons, well, again, protons are located within the nucleus of the atom and maintains a positive electric charge. It is the number of protons within a nucleus that determines what type of element that atom is going to be. Example would be, if you have one proton within the nucleus, you have hydrogen. Whereas if you have 92 protons within a nucleus, you will have uranium. Neutrons, they're located in the nucleus as well, have no electrical charge. Now, it's the number of neutrons compared to the number of protons that determines if an atom is going to be radioactive or not. Again, electrons orbit that nucleus and are negatively charged. The electrons determines the chemical properties of the atom. There is one electron for every proton. Now, this can change should the atom become ionized or bonds chemically with another atom. When the bonding occurs, these atoms form molecules. At this point, these atoms are sharing those electrons. Now, heat will increase the speed of orbit around the nucleus of electrons, whereas electricity is the result of those electrons moving from one atom to another. What is considered stable versus unstable? Well, the number of protons compared to the number of neutrons will determine the stability of an atom. Too many or too few neutrons compared to the number of protons will cause the nucleus to have excess energy, thus making the atom unstable or radioactive. The purpose of an unstable atom is to become stable. It does this by releasing excess energy in the form of particles or waves. Ionization is the act of unstable atoms removing electrons from a stable atom. Ionizing radiation is energy being released by an unstable atom that has the ability to remove electrons from other atoms. Example of ionizing radiation is alpha, beta, gamma, X-ray, and neutron. Non-ionizing radiation lacks the energy to remove electrons from the atom. Therefore, it is unable to ionize an atom. Examples of non-ionizing radiation are radio waves, microwaves, visible and ultraviolet light. Now, radioactivity is the action of radioactive or unstable atoms attempting to become stable by releasing ionizing energy. Whereas radioactive material is any form of matter, again, solid, liquid, or gas, containing unstable or radioactive atoms, which is releasing ionizing energy in the form of alpha, beta, gamma, or neutron. At this point, I want to point out something to you. A lot of times we compare or we combine gamma and X-ray when we're referring to ionizing radiation. The reason we do this is because gamma radiation, X-ray radiation, release their energy in the form of waves as opposed to particles like the other three do. They are two distinct, different types of radiation, yet they release their energy in similar ways. When radiological describes materials that emit radioactive energy, nuclear defines the process of splitting the nucleus through the act of fission or binding nuclei of an atom through the act of fusion and harnessing that energy from that process. Now, let's talk about the types of ionizing radiation. First of all, you have your alpha radiation. It consists of large particles containing 2 protons and 2 neutrons and no electrons. It is positively charged and has the ability to strip electrons from surrounding atoms while passing through the material, and by doing so, it ionizes thousands of atoms. Alpha radiation is not an external hazard due to this easily being blocked by something as simple as a dead layer of skin, and it does not pose a risk to internal organs. The hazard in alpha radiation lies in the risk in allowing that material that emits alpha radiation to enter the body through routes such as indigestion. If this should occur, then the alpha radiation can reach the cell and deposit large amounts of energy in small volume of exposed cells. Beta radiation is a negatively charged particle released from the nuclei at a high rate of speed. It pushes against the electrons of the nearby atoms, thus causing the ionization. Beta radiation has the potential to travel up to 30 feet. A piece of thick plastic, thick aluminum, thick clothing, and thick safety glasses all act as shielding. Your turnout gear makes a good protection against beta exposure. Beta radiation is both an internal and an external hazard. Externally, it has the potential to be a hazard to both the skin and the eyes, but it cannot penetrate the skin and therefore poses minimal hazards to organs if exposed externally. But if inhaled or ingested, it can expose those organ cells to energy deposits. Now, you see this picture here when we talk about this. Again, it is an external hazard, but it cannot penetrate the skin. What you're seeing here is a picture of what we call beta burns as a result of this foot being exposed to beta radiation or beta particles. Gamma radiation and X-ray in similar fashion is different from alpha and beta in the fact that gamma radiation is pure energy. There are no particles involved. Ionization occurs when the electrons in its path are stripped away. A single gamma ray can ionize thousands of atoms within the path of travel. It possesses very high penetrating power and can travel hundreds of feet. It requires very dense material such as concrete, lead, dirt, or steel to prevent penetration. Due to the strength of gamma and X-rays, it will penetrate body tissue quite easily and therefore damage internal organs whether the source is inside or outside the body. Therefore, it is considered a whole body hazard. Neutron radiation occurs when the neutron is ejected from the nucleus. It is a mass that contains no electrical energy. Ionization occurs when the neutron slams into a nucleus and continues forward, crashing into other atoms within its path until the energy has depleted. It can travel several hundred feet and is best shielded by materials with large hydrogen content, such as water. Neutron radiation is considered both an internal and external risk and therefore considered a whole body hazard. It can easily penetrate body tissue and thus can damage the tissue itself. Measuring radiation. First of all, let's talk about radiation dose. Radiation dose is the amount of radioactive energy absorbed by the human body. Now, pictured here is an example of a dosimeter. This is worn by those people being exposed to radiation. And this will determine how much or the amount of radiation this person has been exposed to who is wearing this dosimeter. Radiation dose rate is the dose of radiation energy exposed to over a period of time. Radiation is measured in units defined as retinogen, radiation absorbed dose, or rads, or retinogens equivalent to man, or REMS. A rad is applied to all types of radiation. It's considered a unit of measured dose absorbed by all material, whereas a REM, on the other hand, is a unit of measurement that takes into account the absorbed dose and biological effects on the human body due to different types of radiation. Most often, rams per hour, R per hour, rad per hour, or rem per hour are considered equal and interchangeable. Meaning, should we respond to a radiation incident and you're looking at your meter, it could read in rads, rems, or Rs, okay? What we need to know is what the meter is saying, whether you say it is reading 1,000 Rs per hour, 1,000 rems per hour, or 1,000 rads per hour is irrelevant, as long as we have that number followed by what it's reading. And we'll go in further here in just a second. Most meters measure in doses of either R per hour, milli-R per hour, and or micro-R per hour, as well as, again, rem per hour, micro-rem, or millirem. Now, internationally, and as well as the U.S. military, they measured their radiation doses in the term of sieverts, as opposed to Rs or rads or rems. This is an example similar to the way we do measure distance as millimeters as opposed to inches. Now, this is important because this is what your meter is going to read to you. 1 micro R, micro rem, micro rad equals 1/1000th millirem, millirad, or milli-R. Or if you look at it this way, 1 millirem equals 1,000 microrems, 1 milli-R equals 1,000 micro-Rs, or 1 millirad equals 1,000 microrads. Similar, 1 milli-R, millirad, millirem equals 1/1000th rem, rad, or R. So 1 R would equal 1,000 milli-Rs or millirems or millirads. To put measurement in perspective, it would require a person to be exposed to at least 50 rems before the exposure begins to have a biological effect. Most stopping points or turnaround points, and when we talk about turnaround points, those are recommended stopping points when you're searching out radiation, meaning going no further unless there's rescues involved, at 2 millirems per hour. Now, what happens if you're exposed to 50 Rs or 50 rems or rads? Well, it depletes your white blood cell count. Now, you're saying, well, what does that mean? Let's take hypothetically that you go to work one day and you're starting to have the onset of the flu. Well, if you're exposed to 50 rems during that work day, you're going to have a very bad case of the flu because it depleted your ability to defend against the virus. Now, how do we respond to radiation? We respond by trying to maintain a low as reasonably achievable, or LARA. Now, this is a concept of radiation safety that's goal is to manage and or control the dose of radiation received by an individual. This goal can be reached through the use of time, distance, and or shielding. When we talk about time, we talk about the less time an individual spends exposed to a radioactive source, the less opportunity energy has from the radioactive source has to damage the tissue. Now, let's remind ourselves, there's a difference between exposure and contamination. If I am standing near an isotope or a form of matter that is emitting radiation energy, I'm exposing myself to that radiation. If I were to swipe my hand and the radioactive material is a dust and I get that dust on me, now I am contaminated with that radiation. Distance. The distance an individual can place between themselves and the radioactive source, the less radioactive energy a person will be exposed to due to the strength of the source diminishing as it travels over that distance. Example of this is alpha particles travel only inches. Okay, whereas beta, there are certain beta isotopes that can travel up to 30 feet. And again, gamma and X-ray travel hundreds of feet as well as neutrons. Shielding, placing objects that can obstruct the flow of the energy from radioactive sources can reduce or eliminate the amount of damage to tissue as a result of exposure. Now, like I said before, alpha particles are very weak, so therefore they cannot penetrate dead layers of skin, so paper is a good blockage for alpha source. Whereas beta, again, your turnout gear, it needs to be a little denser, a little thicker, but it can block beta source as well as gamma, or excuse me, as well as alpha. Now gamma and or X-ray require thick concrete, lead, or dirt. The same with neutron, thick plastic, large amounts of water. When we talk about large amounts of water, we're talking about large amounts of water with high, and this is based on the fact that there's the hydrogen count within the water. How do we know we're on a radioactive incident? Well, first of all, if we're responding to an incident on the road, we look for placards just like we do any other hazardous material incident. Placards are required on vehicles transporting radioactive materials and should be visible from all four sides. Labels are required on packages containing radioactive materials. These are separated into three categories. Category 1 being a material emitting the least amount of energy. Example of that would be the maximum amount Category 1 package can carry should be able to read 0.5 millirents per hour at the box or at the package. Whereas Category 2 can read up to 50 millirents per hour at the surface of the package and 1 millar per hour at a distance of 1 meter. Now, Category 3 emits the highest amount of energy with the maximum amount of 200 millars per hour at the surface of the package and 10 millar per hour at a distance of 1 meter. Now, physical labels are for those packages containing those physical materials used in nuclear activities, whereas empty label is for those packages that at one time carry radioactive material and may have residual readings. You can also identify radioactive material through the packaging. There are basically three types of packages, but we're going to discuss two of them, A and B, because B and C are so similar. Type A packages carry non-life-threatening levels of radioactive material and are designed to withstand normal shipping incidents. Now, this doesn't include traffic accidents. Whereas Type B and also Type C packages are designed for hazardous level radioactive material and are able to endure accidents both automobile and in shipping, as well as fire. There are many different types of Type B packaging. If you have any questions concerning radioactive or any questions concerning anything, please don't hesitate to contact me through jfdbanta@gmail.com or call me here in the classroom. Other than that, I look forward to continuing the process and getting you guys trained on your new equipment. Thank you very much.